Hello everyone and welcome to CCNA Scaling Networks version 6. Today we're looking at Chapter 6, EIGRP, Enhanced Interior Gateway Routing Protocol. So we're going to look at features and operations of EIGRP, different types of packets. We're going to look at the algorithm, the dual algorithm, and then we're going to have a look at how we configure it for IPv4 and for IPv6. So, EIGRP was first invented by Cisco. They first created IGRP as to try and combat with RIP, and then OSPF came along and they very quickly realized that they needed to improve it. So they went from Interior Gateway Routing Protocol to Enhanced Interior Gateway Routing Protocol. In recent years, they've realized that OSPF is pretty much everywhere in the marketplace, so they've submitted an application to have it go open standard. So technically EIGRP is Cisco proprietary, but it's in the process of becoming an open standard. It uses the main characteristics of distance vector, which is looking at the neighbor information from the neighbors. The update algorithm is called dual, diffusing update algorithm. It has neighbor adjacencies, and it uses a very special thing called reliable transfer protocol. We'll talk about that in a minute. And it doesn't, unlike RIP, where RIP sends the entire route table every 30 seconds, EIGRP can send partial or bounded updates, so just what's needed, and supports different types of load balancing. Reliable Transport Protocol is the way that EIGRP uses to talk, and this is the most important part, one of the most important factors in EIGRP, because RIP needs TCP/IP to function, OSPF needs TCP/IP to function, BGP needs TCP/IP to function. EIGRP does not. You can have, if you've got a router running IPv4, then it has the IPv4 protocol dependency, then it uses this reliable transport protocol, and then IPv4. If you're running IPv6, you can run pure IPv6. If you're running AppleTalk, if you're running DECnet, it doesn't matter. The reliable transport protocol means that EIGRP can run on pretty much any routing protocol you can imagine. However, the throwback is, or the downside is, that if you've got 4 routing protocols, then you've got literally 4 times the amount of memory and processing power being used by EIGRP, because EIGRP maintains 3 basic tables: the neighbor table or adjacency table, the topology table, where all the links are, and then the routing table is the best and second best paths. And that's what it gives to the router. It gives it the best path. EIGRP supports authentication, which is a really useful tool. But this is not encryption. This is a way we can set up a trust to say, yes, router 1 trusts router 2, router 1 trusts router 3. So you can still sniff out these packets, and you can still learn how the network's put together. But it's impossible to inject any false information, because every routing update is authenticated with the hash algorithm. So it's not to stop people learning about your network, it's to stop people injecting bad or false information. So let me clarify. It's an authentication method. The encryption is the password, but the actual data itself is not encrypted. 5 basic types of packets: hello, acknowledgement, update, query, and reply. Now, hellos and acknowledgements are set unreliable. They're just sent off, and that's good. Whereas an update or a query or a reply must be acknowledged. Very, very similar format to the classic sort of TCP. EIGRP uses multicast. So RIP version 1 uses broadcasts, RIP version 2 uses multicasts. EIGRP uses multicasts. So RIP uses 224.0.0.9 and EIGRP uses 224.0.0.10. And thankfully, when you're looking at the difference between IPv4 and IPv6, you don't have to memorize the IPv6 address, because 224.0.0.10 is equivalent to FF02:A, 10A. Hellos are sent every 5 seconds by default on normal networks, unless you have a slow link. So if you've got a 1.5 meg link or slower on a non-broadcast multi-access like frame relay, then the hellos are sent every 60 seconds. And the default hold timer is 3. So if two routers have an adjacency and they haven't spoken for 15 seconds, they will realize that there's a problem and the adjacency will be broken. The RIP sends the whole route table every 30 seconds, but EIGRP keeps a track of what's changed. So if a router wakes up and says, hey, I've got revision 27 of the route table, and another router says, well, we're actually up to revision 29. So the router can say, oh, well, can you send me just what's changed? So it's a partial update. And I can also send bounded updates, which means I only send the updates in a certain direction that need to be sent. I don't have to send it everywhere. I can just send what you need to know what needs to know it. And these updates are sent reliably. So queries, responses, and updates are all sent reliably, which means they require acknowledgement. So router 2, he says, guess what guys, one of my networks gone down, here's a piece of information. Both router 1 and router 3 acknowledge that they've received that information. Reliability. This is just the basic anatomy of an EIGRP packet. They used to have these questions in the exam, but I don't think they're on there anymore. But the most important thing is this is the autonomous system number. The AS number must be consistent throughout all your organization. So if you've got 10 routers and you say router EIGRP 101, that number 101 must be the same on every single router. Now, autonomous system numbers are legal registered values, but thankfully there are a bunch of numbers way up high in the 65,000 range that are considered private. So technically, if you're just doing a bit of lab work, you can just say router EIGRP 100 and everyone can use 100 and everything's fine. But, just to be a bit more professional, they want you to use those private numbers, private AS numbers up around the 65,000 that no one has registered. All right, let's have a look at how we actually program the equipment. So, configuring EIGRP. So we go router EIGRP 123. 123 being the autonomous system number. Must be the same on all routers. Then we type in the network. 192.168.10.0. This is identical to the way we configure RIP. This is the list of networks that we are going to advertise. Now here's one thing that we have to take very particular care of. The bandwidth command. Notice that the bandwidth command goes on each interface. This command, bandwidth, is a way that we manipulate routing protocols to teach them the speed of a connection. For example, if you have a connection where it's a gigabit connection to your ISP, but your ISP shapes you down to 100 meg, EIGRP is going to look at that gigabit connection and say, oh, this is a gig. So I'm going to tell everyone, hey everybody, I've got a gig to the internet. So you have to type in the command bandwidth to trick it and say, actually, you know what, it's 100 meg. But one of the interesting features of EIGRP is that you can tune it. So you can say, listen, EIGRP, I know you got a lot of work to do, and I know you got a lot of information you got to send everywhere, but from now on, you're only allowed to use 25% of the available bandwidth in order to say what you want to say. So for example, that gigabit connection to our ISP, but realistically we've only got 100 meg internet, if the default is 50%. So if EIGRP's got information, it'll look at that link and say, oh, this is 1 gig, and it'll just smash it with 500 meg worth of updates. But this command is quite useful because you say, no, we only want you to use 25%, or this example 25%, of the total available bandwidth on each link. By default, EIGRP likes to summarize. Actually, I'll clarify that in a few slides' time. So it's a good idea to turn it off. So if you're doing variable length subnet masking, or you've got some very bizarre addressing scheme, then turn off automatic summarization. So it basically treats all the networks as classless. And if you want to be super specific, we can put the mask on the end. Notice here 192.168.1.64, 255.255.240. That way we're only just advertising this one specific subnet. Now recently there's been an update to EIGRP where you can have either a real normal mask of 255.255.255.240, or you can have an inverse mask or a wildcard mask. Now, nothing to be afraid of with inverse masks or wildcard masks. They are literally just a mirror to the value. So a mirror of 255 is 0. A mirror of 240 is 15. So you just get all the ones and the zeros and you reverse them, swap them over. Or if you want a little cheat shortcut way of figuring out, the inverse mask is the difference between the first number and 255. So 255, 0. 255, 0. 255, 0. How many do we need to count from 240 to get to 255? 15. The difference between 255 and 240 is 15. Summarization is a really interesting factor because routers want efficient route tables. The smaller the route table, the happier the router. And in EIGRP, make a special note too that the summary command lives on the interface. So this is where we're aiming or pointing the summary. IP summary address 123. The other interesting thing that EIGRP does is that if you've got multiple networks behind the same class system or subnets of the major network, you don't have to put the whole thing in. So 172.16 literally could advertise all your subnets behind that. And 192.168.10, if you've subnetted that 10 times, EIGRP will automatically summarize those. But you just have to remember you have to actually advertise the networks you want to advertise using the network command. Now the router ID isn't super critical in EIGRP. It doesn't play much of a role, but in OSPF it's a big deal, and we're going to look at that in 2 chapters time. But just know that the router ID is there, and it can either be dynamically sorted out all by itself, or you can manually set it with the command. Notice where we are, the routing process, EIGRP, router ID, and a 32-bit IPv4 address. Passive interface command. We haven't talked much about the passive interface command yet, but the passive interface command says do not send routing information out of this interface. It'll still learn and it'll still hear, and there's a lab that you'll do that will show what happens when 2 routers, one is passive and the other isn't. Both routers learn. The one that's passive will still learn things, but won't ever share, has nothing, it can't talk. So you can set up a passive interfaces. Simple and easy way to verify how many passive interfaces you've got or what they are, show IP protocols. Super useful command, and pretty much from now on, whenever you're doing any routing using a dynamic routing protocol, show run is slow. Takes too long to find what you want. Show IP protocols, everything you need to know on one big screen. So let's have a look now. Neighborships. I mentioned before that EIGRP has 3 tables: the topology table, the routing table, and the neighbor table. So this is the list of all of the immediate neighbors that it has. So router 1 in this example has got 2 neighbors: 192.168.10.6, 172.16.3.2. They're visible by the serial interfaces, hold down timers, because these are probably slow links, so they're 60-second timers, and the amount of time they've been visible for. So if 2 routers aren't talking and you can't understand why, show IP EIGRP neighbors is a good way to see who can see what neighbor. Alright, let's have a quick look at how EIGRP is put together. We've got 2 routers, router A and router B. Router A wakes up and sends out a hello, a multicast, 224.0010. That's an EIGRP hello. Is there anyone out there running EIGRP? Router B receives that hello and says, hey, here's my update. Here's my routing table. And of course, because it's an update, it must be acknowledged. So we send an acknowledgement. Now these 2 can see each other. and router A has the topology that he's learnt from router B. Then router A says, you know what? Here's my route table. Here's all the stuff you need to know about me. And, like all updates, must be acknowledged. And now we have convergence. Router A and router B, they've said their hellos, they've seen each other, they've updated and acknowledged, and they are formed a neighbor adjacency. The metric. The metric is comprised of 5 possible values. And these are called Ks, the 5 K values, K1, K2, K3, K4, K5. Bandwidth, delay, reliability, load, and MTU are the metrics that are put together in this giant composite equation to generate how all this is put together, and it's all a big long value, and it's all a bit messy, so let's just summarize it. EIGRP is just bandwidth plus delay. EIGRP, they wanted more granularity. So it's bandwidth times 256 plus delay times 256. So some of the metrics you'll see when you've got a serial link running at 2 meg will be 3 million. It's just a really, really large number because EIGRP wants to have that granularity. And remember that the bandwidth is automatically discovered based on the physical default interface speed, unless you use the bandwidth command. And that's why it's always recommended to set up the bandwidth command, because you might have a 2 meg serial interface, but you may have the clock rate set at 64K. So therefore you have to type bandwidth 64 so that EIGRP knows exactly what it's doing. The diffusing update algorithm. Loop-free, fast convergence, very efficient. So let's have a look at the finite state machine. It's basically the brains behind how EIGRP puts itself together. We'll show it maintains a list. The interesting thing that Joule does, which is quite clever, is it calculates all the best paths, the best, most efficient paths to get everywhere, and it calculates the second best path to everywhere. And in this way, not only does it guarantee a loop-free topology, but the second a primary link fails, the backup link can take over almost immediately. So let's have a look at the show IP route. We have the feasible distance, or the metric. So the administrative distance is 90, and a big capital D to show that it's EIGRP, and the feasible distance is the actual metric. So what do we got there? 3,012,096. That is the metric. That is the feasible distance that it's going to take to get to this network from this router. And we've learnt it via 192.168.10.10. So that is the successor. Now, if we look at the topology, however, we notice that actually, look, EIGRP says, you know what, I can get to 192.168.1.0 two ways. I can get there via 192.168.10.10, and I can get there via 172.16.3.1. However, the feasible distance for the top one is 3 million, but the feasible distance for the second one is 41 million. So clearly that's not as good as the current successor. Therefore, when you do show up here out, you only see the best one. But EIGRP has both the best and the second best waiting in the wings to go. Now there's this horrible sentence right in the middle that's very confusing, but we'll cover that in a bit more detail. So the best is the best because it's the best, 3 million. Now the second best is when the reported distance from the neighbor is less, this one here, so this is what these two numbers are. This is the distance that you can see, the total feasible distance, and the second value is what your neighbor has told you is their feasible distance or their reported distance. So here, the reported distance from our neighbor is 2 million. So when the reported distance is less than the current feasible distance of the successor, then this route is flagged as a feasible successor, a second best. So if for some reason serial 00/1 fails, instantly this will be given to the router and put into the route table, and then EIGRP will go away and try and figure out what it can do to keep going on with its routing. Here it is. So here we have router A has 3 paths to get to network 24. Let's have a look. So this is the topology table. We've got, to get to network 24, the feasible distance via RTX is 40. The feasible distance by router Y is 31, and the feasible distance via router Z is 230. So let's prove that out. So let's go for the bottom one first. So this link is 10, plus 100 is 110, plus 100 is 210, plus 10 is 220, plus 10 of network 24, 230. So notice that the feasible distance and the reported distance. So let's look at the top one. So we've got 10, 20, 10. So therefore this one, router X, says, hey, I know network 24. If you want to come via me, he's 30. So the reported distance is 30 and the feasible distance is 40. So let's look. Now obviously the best one is here through this FDDI, fiber data distributed interface connection through here. So this is the topology table. 3 possible ways. One, this one via the middle is the successor, and via the top is the feasible successor, because the feasibility condition exists, because the reported distance is currently less than the feasible distance of the current successor. I'll say that again. The feasible successor does exist because the reported distance is less than the feasible distance of the current successor. So EIGRP says, zoop, routing table, this is what you need. One route via router Y. But the tradies out in the street have dug a hole and they've dug up our fiber optic cable. So now the successor's gone. No more successor. So thankfully we had a feasible successor. So instantly that is promoted. The feasible successor becomes a successor, and now EIGRP gives the route table, says, you know what? You can still get to network 24 via router X. And then it goes away and does queries, help me, how do I, is there any way better? And unfortunately there isn't, because look at the feasibility condition. The reported distance from router Z is 220, and that is not less than 40. So therefore there is no feasible success. So just a bit of a breakdown of the finite machine as it does its work. Lost connectivity to the successor. Is there a feasible successor? Yes or no? If there is, bang, promote it, put it in the right table. Then start selecting that successor, then go for it. If there's no feasible successor, then place the destination in the active state and start asking all our neighbors with queries, yo, how can we get to this network? If the neighbor knows how to do it, then he'll answer and say, yes, please. And then here's your information. If it does not know the answer, then it will remove from the topology table. Now this is a very interesting word we used here, the word active. Place destination network state in active. It might sound a bit weird, but when a routing protocol is active, it's really bad, because that means it's doing work. Routing protocols shouldn't do work. They should make the decision and tell the router, this is what you should do, and then that's it. Sit back and go to sleep. So when EIGRP is running perfectly, it's not doing any work. Just every 5 seconds it sends a little tiny hello. That's it. It doesn't have to think or calculate. But when it's active, that means it's in trouble. It's desperately looking for something that it doesn't know. So just a little sort of a backwards bit of terminology. You're going to see when we get to BGP as well, when a route is active, that's bad, because it means it's desperately looking for it. All right, EIGRP for IPv6. So exactly the same as IPv4, 3 tables: neighbor table, topology table, routing table. IPv6, exactly the same. Nothing, no big surprise there. Let's look at the comparison. EIGRP for IPv4, EIP for 6. Same, 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 same. There is only one, obviously the multicast address 224.0.0.10 FF02:A. It's different, but it's the same. It's A and it's 10. 10 is A. The only thing at the bottom is the router ID. The router ID can be dynamically generated in IPv4 because IPv4 has lots of stuff. However, IPv6, it has to be manually configured. And that's a little caveat with configuring EIGRP is you have to manually set the router ID. If you don't manually set the router ID for IPv6, EIGRP struggles. Remember your link local address. Your link local address, you can leave it set to dynamic if you want, and that's absolutely fine. But it's a lot easier if you set it. So remember, the link local address is only used for that local multicasting to replace the ARPs and the RARPs. So it's a best practice to set it. Just so you don't have, if you want to ping from R1 to R2, you can just type ping FE80:2 instead of FE80:1234:4567:ABCD: the big long IPv6 address. That's dynamic. So whenever they're multicasting, this destination is FF02A and the source is whatever the link local is. So we need to first turn it on. Good old IPv6 unicast routing. That's the universal command that should be on everything you ever do with IPv6. You got to turn it on. Then IPv6 router EIGRP and a number. Once again, that number is the autonomous system number, and that number must be the same on all of your equipment. Then we give a router ID, and that's why the no shutdown command is there, because if you don't have the router ID, EIGRP can't begin. So you have to give it a router ID and then turn it on. Because if you just type IPv6 router EIGRP2 and press enter, it will try and start, but it will break because it doesn't have a router ID. So you give it the router ID and then you type the no shutdown command to actually get EIGRP started. Now, just like RIP, in RIP version IPv4, we have network statements. In RIP for IPv6, we put those commands on the interfaces. Exactly the same for EIGRP. EIGRP IPv4, we have network statements. EIGRP for IPv6, the commands go on the interface. So IPv6, EIGRP, and the autonomous system number. In this example, it's just the number 2. And that's it. That's all you have to do. So you got to remember IPv4, network statements, IPv6, commands in the interfaces. Same thing for the neighbor table. Show IPv6 EIGRP neighbors. Exactly the same. These are my neighbors. These are the interfaces. This is how long I've known them for. Exactly the same command. Nothing special about it at all. Show IPv6 protocols, just as useful as show IP protocols. You've got your autonomous system number, you've got the K values, you've got your router ID, you've got your administrative distance, you've got which interfaces are behaving in EIGRP IPv6. Exactly the same as IPv4. Show IP protocols, show IPv6 protocols. Exactly the same. Alright, so we looked at EIGRP and what it can do. It uses Joule for its update algorithm. The default administrative distance is 90 and external routes are 170. We'll look at that in more detail in a little while. Joule has neighbor relationships. It uses reliable transport protocol. It can send partial and bounded updates, and it supports different types of load balancing. Protocol dependent modules mean that it can do IP, IPv4, IPX, AppleTalk, DetNet, everything. It uses hellos for discoveries. It forms neighbor adjacencies. The metric, it's got 5 values that it can use: bandwidth, delay, reliability, load, and MTU. But typically, and you shouldn't change it, you just use bandwidth and delay. And the finite state machine, or the brains or the guts of the EIGRP, uses the successor is the best path, and the feasible successor is the second best path. Alright everybody, thank you for your time, and I'll see you in the next one.